Okay, welcome everyone. Welcome to Abu Dhabi. Welcome to the United Arab Emirates. Welcome to NYU Abu Dhabi. It is with great pleasure that I welcome you all to Strings 2025 in Abu Dhabi. Strings is the flagship conference of the global string theory and theoretical physics community. Over the past 34 years, Strings has been held in various cities across the globe, and this year it is here in Abu Dhabi, marking a historic event of being the first Strings in the Arab world. For making this achievement happen, I'm indebted to the President of the United Arab Emirates, His Highness Sheikh Mohammed bin Zayed Al Nahyan, for his vision driving the UAE to where it is today. I would especially like to thank Vice President, Deputy Prime Minister, and Chairman of the Presidential Court, His Highness Sheikh Mansour bin Zayed Al Nahyan, for his special attention into making this conference a reality, and for his generosity and support for this conference and similar educational and scientific initiatives, pushing Abu Dhabi to the forefront of science and research. The UAE is a leader in supporting sciences and scholars. For decades, its government has been providing an inspiring environment for innovation and research to achieve sustainable development. On a personal note, I would also like to thank the Scholarship Office at the Presidential Court for sponsoring me and supporting my academic journey throughout the past years. This support has played a significant role in enabling me to achieve my educational aspirations. I shouldn't forget to thank my home institution, NYU Abu Dhabi, for their support and hosting of this conference, and for being fully invested into organizing the very complicated logistics into ensuring the success of Strings 2025. NYU Abu Dhabi is itself an achievement, about which you'll hear more from my friend and colleague, Provost Arlie Petters. Finally, I'm obviously extremely excited about the science that will be discussed here this week. We're privileged to have a stellar list of speakers and participants in attendance, which I hope will make this a watershed event, bringing new insights into how the world works. For the students and non-scientists in the crowd, I hope you also get something out of this conference. You'll get a chance to see what scientific exchange looks like, and as a heads up, it's going to be intense, but exciting. Before I hand it over to Arlie, I wanted to make just two quick announcements or requests. If you haven't signed up for the gala dinner, please sign up. And if you haven't signed up for the outing, also please sign up. And with that, let me hand it over to Arlie.
Good morning, Your Excellencies, honored guests, friends from here and abroad. What a delight to start out Strings 2025. I learned from Ahmed that this is the 35th annual Strings Conference, and indeed, as he noted, the first to occur in the Arab world. It is therefore a pleasure and a privilege for us to play host for such an important gathering. Indeed, there are several hundred participants, including here some 320 coming from some 56 different countries. It is a representation that reflects the ethos of NYU Abu Dhabi, where we see ourselves as a global liberal arts and research university, welcoming those from all over this planet, coming here with different ways of knowing. Indeed, among the stellar panelists and participants, we'll have a myriad of expertise exploring connections between quantum information theory and holography. Some will explore deeper understanding of spin theories and thermalization in holography. Some will also do extensive work on the topological string theory and its mathematical foundations. And as I say all these topics, and this was something that was alluded to, gatherings of this sort are also not only for the world's very best, but we're hoping that it will also distill pedagogically into the spaces that Ahmed mentioned, where we have our undergraduate students that I know will also welcome these different ways of penetrating the structure of our known reality. I also would like to add that and extend my thank you to the Scholarship Office of the UAE Presidential Court. This initiative was founded by His Highness Sheikh Mansour bin Zayed Al Nahyan. The SCO offers scholarships to exceptional Emirati students at top local and international universities, supporting the UAE's development by preparing highly qualified nationals to contribute to the country's progress, a progress that is anchored around developing a knowledge-based, dynamic economy. As a university in and of Abu Dhabi, NYU Abu Dhabi is surely proud, as I said, to be a host of this very important and unique conference within the Arab world. I add that as a young university, some 14 years old, and also a university supported by His Highness, we are very proud by the excellence that has already been achieved over this short time. Some 22 Rhodes Scholars, and over the past few years, we have hired 3 Nobel laureates. And so your presence adds to this excellence. It adds to a synergistic hub that we know will continue to catalyze the great efforts for NYU as an anchor institution serving the country, serving the UAE, the region, and the world. And so I want to highlight again how important it is that you have come in person, and many of you are here online, and how much we value and cherish this kind of intellectual fellowship. So thank you, and enjoy the next few days of the conference.
Okay, so we're going to get started. So let me first introduce the chair of the next session, Leonardo Rastelli. Please come on the stage. All yours.
Thank you. So welcome, everybody. So the first session will be the first of the review plus panel. So there will be a 40 minutes review by John McGreevy on generalized symmetries in condensed matter and the Landau Paradigm, followed by 5 minutes of questions. Then will be 3 short presentations, 5 minutes each by the panelists, and then there will be panel discussion, and then at the end there will be questions from the audience. So it's my pleasure to introduce John McGreevy from UC San Diego, who will give the review.
How do I advance my slides? This seems to be the only available tool. Does anyone have any suggestions? Thank you. So thanks for having me. My task is to report back to you from 15 years or so of being embedded with the condensed matter theorists on ways in which ideas about generalized symmetries have been useful there, and hopefully convey some insights that will be interesting to string theorists. I want to start by emphasizing commonality of purpose between these fields. A big goal in condensed matter physics is to characterize and understand phases of matter. And what's a phase of matter? Well, our best definition is that it's the basin of attraction of a fixed point over the normalization group. And a stable phase is associated with a fixed point, which has no relevant perturbations. And about this definition, I want to emphasize two things. The first is that this is the same goal that one would have if one wanted to understand quantum field theory. And the second thing is that a priori, this definition has nothing to do with symmetry, except maybe something about scale invariance, since I mentioned fixed points. And so that makes a strange situation that our best answer to this question very crucially involves symmetry, and it comes under the name of the Landau Paradigm. And I think it's fair to say that at least by volume, that's led to most of our understanding of condensed matter physics. It's the statement that phases of matter should be understood in terms of their symmetries. I guess a slightly more specific statement of it is that they should be understood in terms of which of their symmetries they spontaneously break. And maybe an expectation that goes along with that is that if we have a stable phase that has some gaplessness or degeneracy, that those modes should be swept out by a spontaneously broken symmetry. They should be Goldstone modes. And about this, I want to emphasize that it's a conjecture. It's an incredibly successful conjecture, but nevertheless it's a conjecture. And it has some apparent exceptions, which have been essentially the subject of modern condensed matter physics for the last 50 years, about which let me give a brief summary from a non-symmetry perspective. So in the special case of a gapped phase, another useful way to think about it is as an equivalence class of Hamiltonians, where two Hamiltonians are in the same phase if we can get from one to the other by adiabatically deforming, get from the ground state of one to the ground state of another by adiabatic deformations combined with tensoring in product states. And so two phases are different if they're separated by one of these walls of gaplessness here that I've drawn in red. And this definition emphasizes a crucial difficulty of the problem, which is that this space that I've drawn here in 2 dimensions is actually a very, very high dimensional space. And if I give you 2 points in it, it's very difficult to tell whether or not you can get from one to the other without having to pass through the wall of gaplessness. And the crucial idea, of course, for labeling phases is then to find invariants, quantities that can only change by jumping and can't change under adiabatic deformation and tensoring in product states. So such a thing is necessarily a topological quantity. And the most basic example of such a quantity arises from if we spontaneously break a discrete symmetry. So here's a picture of a system that on the right, it has a Z2 symmetry that it doesn't break and therefore has a unique ground state. And on the left, it has a Z2 symmetry that's spontaneously broken and therefore has 2 ground states. This number of ground states is an integer. The only way it could not be an integer is if the gap closes and a whole bunch of states pile on top of it. This isn't the only possible topological invariant by which we can distinguish phases, and states that are distinguished by something else other than symmetry breaking are called topological states. And they come in 2 classes. There are ones with topological order and ones without. And so what is topological order? Well, a good definition of topological order, a state has topological order if it has excitations, which are localized excitations like particles, which nevertheless are not created by any local operator. Rather, they arise, say, at the end of some extended operator. And the fact that these excitations are not created by a local operator means that they can carry fractional quantum numbers, fractional spin, fractional statistics, and various other data, collections of integers that can be used as labels on the phase, things that can't change under adiabatic deformations. And a good picture to have in mind of how such excitations arise is this cartoon wave function at the top right there. Imagine that the ground state wave function is a superposition of closed strings. So there's some energetic condition that says that these strings don't want to have endpoints. And in a state where they nevertheless do have endpoints, those endpoints represent localized clumps of energy, some kind of particle, which of course can't occur on their own because they are defined as the ends of these strings. Okay. Another important symptom of topological order is that if I put the system on a space with non-trivial topology, it has a number of ground states that depend on that topology. And these ground states arise by acting on a reference ground state with the holonomials of these particles, with the closed strings in these pictures. And very crucially, this means that these ground states are locally indistinguishable from each other. There's no local operator that tells one of these ground states from another, which is important for the fact that this is a property of the phase. It's a stable property. If there were a local operator that distinguished one of these ground states from the other, we could add it to the Hamiltonian. It would split this degeneracy. Okay, there are states that are non-trivial, that don't break any symmetries, and that don't have any topological order, and I'll come back to them in a little bit. So there's a list of exceptions to this Landau paradigm, of which I've said a little bit about one class of the exceptions. And the idea that I want to talk to you about is the idea that perhaps by generalizing what we mean by symmetries and using them more thoroughly than we have before, we can understand all of these apparently beyond Landau phases in terms of a suitably generalized Landau paradigm. And this story has two ingredients. Uh-oh. My button is not working. Do you know why my button isn't working? I don't think I did anything. Okay, thank you. Okay, so the two ingredients are generalizing what we mean by symmetries and taking advantage of them fully in the form of a Toft anomalies. So let me talk about the second thing first. So I probably don't need to tell you what an anomaly is, but let me give a very general definition. Suppose we have a system with a symmetry. There is a somewhat systematic procedure for coupling it to background fields. That procedure involves some arbitrary choices, like a choice of gauge. When physics depends on that choice, say physics in the form of the partition function, we say that there's an anomaly. And this idea took a while to catch on in condensed matter physics for various reasons, but also in condensed matter physics, one of the crucial things that we want to know is what is the relationship between the short distance description of some physics and the long wavelength description, and the fact that this transformation of the partition function is manifestly invariant under the normalization group that relates those descriptions, convince people that it's a very valuable thing. In what I've done above, I'm merely deforming the theory by coupling to background fields. I'm not gauging the symmetry, because these are static background fields, but you can see that if there is such an anomaly, it can be regarded as an obstruction to gauging the symmetry. Okay, so a class of phases which are non-trivial, but don't spontaneously break any symmetries and don't have topological order, are called symmetry-protected topological phases, SPTs. And such a thing is a non-trivial phase of matter with some symmetry G, which doesn't do any of these other things I mentioned already, but it can be nevertheless be non-trivial, and it can be characterized by what happens what happens at its edge. And the idea is that the edge theory has some anomaly for the symmetry G, and this anomaly can be used as a label on the bulk phase. Such things actually exist. Let me, as a simple example, let me talk about the integer quantum Hall phase, regarded as a SPT for charge conservation symmetry. So we have a U1 symmetry in 2+1 dimensions. We can solve the current conservation condition by introducing a vector potential, a gauge field. In the absence of time reversal symmetry, the effective action for that gauge field can have a Chern-Simons term. I can couple it to a background field capital A, and under a gauge transformation of that capital A, this action is non-invariant in the presence of a boundary, and the transformation of this action is exactly the contribution from the chiral anomaly from a chiral edge mode, a chiral Fermion mode. So the idea is that the variation of the bulk action cancels the anomaly of the edge theory. And in order to match this anomaly, the edge theory can't be trivial. It has to do something interesting. It can be gapless. It can break the symmetry. And in high enough dimensions, it can have some kind of anomalous topological order. And such an alternative is sometimes called an LSM theorem. And by now, there's a very sophisticated mathematical classification of SPTs in various dimensions for various groups. And in terms of the topological theory of the background fields, and what I want to say about it is merely that we're labeling these phases by how they represent their symmetries. We're still using the symmetries to understand them. So I'm counting this as success for our program. And Maissam will actually give a better way to think about SPTs using symmetry than what I've described here. Okay, the second ingredient is to generalize what we mean by symmetries. So if we have an invariance of a Lagrangian, Nether tells us that that means that we have some topological defect operators. A way to think about the conservation law is that these operators are topological. The fact that transformations of fields satisfy a group law implies that these operators satisfy a fusion rule. And let me give the word topological defect operator is kind of scary sounding, at least to me. So let me give a very concrete example in the context of the classical Ising model. So imagine we have a physical system defined by a path integral of spins on a lattice, two valued variables, governed by, say, this nearest neighbor Ising action. I can define a topological defect operator associated with the non-trivial element of the group Z2, which is it lives on any closed codimension 1 locus in the dual lattice. And it's an instruction, I insert it into my path integral, it's an instruction to flip the sign of J, of the coupling J, for any bond that crosses that surface. And it's topological in the sense that if I deform my surface by dr there, to some other region, I can get the same answers, say for the partition function, simply by redefining the spins from sigma goes to minus sigma in that region. You can see that if instead I were computing a correlation function of a spin in that region, I would get a minus sign, and in that sense, the spin operator is charged under this symmetry. So by now that this perspective has really taken hold, that the topological defect operator is really the thing that we need as a sufficient condition for symmetry. It allows us to treat different kinds of symmetries on the same footing, and of course it allows generalizations. The first generalization I want to mention is that we can change the codimension of the topological operator. Rather than being codimension 1 in space-time and counting particles, where the charged operators are local operators, as in the example I just gave, we can consider higher codimension surfaces, which instead count charged objects that are linked with those surfaces. So say a one-form symmetry, the thing that's charged under it is an operator that would create strings, and it transforms by a phase, which is determined by a closed one form in this case. So I want to take a minute to emphasize that even in the case of zero forms, this generalization is slightly non-trivial. So the analog of that condition that the transformation of a string operator is a closed one form is that the transformation of a local operator is by a phase which is determined by a closed zero form. A closed zero form is just a number if space is connected. But consider the following example. Consider the phenomenon of coarsening. So take a configuration of the Ising model at infinite temperature. That's not, okay, something like the thing on the right. And evolve it by the metropolis rule at a temperature below the ordering temperature. So the thing that happens is the domains form, and actually if I could click on that, can you click on it? Click on the picture. Let's see if it'll work. You'll see what happens. The domains grow, their boundaries have, the domain walls have a tension, and they, and therefore will try to shrink, and there are two fixed points which are all spins up and all spins down. Okay, so I guess we can't see the movie. But now suppose instead, okay, wait, okay, that's okay, but now the clicking isn't working. Okay, there we go. So, but now suppose instead we only do the updates in a non-convex region, so a region with a bottleneck. Then the thing that happens instead is that a domain wall can be trapped near the bottleneck, and when it tries to shrink, it gets stuck there. And so now there are 4 stable configurations, all up, all down, up in the top, down in the bottom, and vice versa. And the thing that protects the lifetime of these 2 extra configurations is the presence of an approximate generalized symmetry. If the neck really pinches, I can independently flip the spins in the top component and the bottom component. There's a non-trivial closed zero form. Okay. So I think many of you probably know that gauge theories, which don't have, whose charge lattices are not maximally filled out by degrees of freedom, have exact one-form symmetries, either, say, U1 gauge theory with no magnetic charges, or non-abelian gauge theory, or other kinds of gauge theory with non-minimal electric charges. In condensed matter physics, higher form symmetries are generally emergent. So for example, in an order phase, such as, say, let's think about a superfluid film. So a system in 2+1 dimensions that spontaneously breaks a U1 symmetry. There is an emergent one-form U1 symmetry whose charge is the winding number of the Goldstone mode. This is the thing that counts the number of vortices inside a loop, and the charge operator is the thing that creates a vortex. In higher dimensions, this is a D-1 form U1 symmetry. And it's not an exact symmetry because the system could have dynamical vortices. And in other condensed matter systems, higher form symmetries also emerge, and I'll say a little more about that in just a second. And this has been a fruitful idea because any question we can ask about ordinary symmetries, we can ask about higher form symmetries, or any kind of generalized symmetry, and in particular, they can be spontaneously broken. So an ordinary symmetry is spontaneously broken if a charged operator has an expectation value. Local operators create particles, and so we interpret this as particle condensation. A one-form symmetry is spontaneously broken if a charged operator has an expectation value. Now the charged operators create strings, and so this is some kind of string condensation. And I've described symmetry breaking in terms of the existence of long-range order, but I want to emphasize that it's possible to prove in a way that doesn't depend on the support of the operators, that the existence of such an expectation value for charged operators implies that the ground state has to transform in an interesting way under the broken symmetry. Okay, that's the proof. I hope you all understood it. So one nice thing is we can solve the mystery of why is the photon massless. The gaplessness of the photon can be understood as from the fact that it's a Goldstone boson for such a spontaneously broken U1 one-form symmetry. And some kinds of topological order can be understood as spontaneous breaking of a discrete higher form symmetry. The idea being that one ground state is related to another one by the action of these topological operators. And because those topological operators are not local, these ground states are locally indistinguishable. So for example, we can think about ZP gauge theory or the toric code in d space-time dimensions, and this has an algebra of electric and magnetic flux surfaces, which has no one-dimensional representations. And here the U's are the higher form symmetry operators, and the V's naively are the operators that are charged under them, and the extra ingredient is that those charged operators are also topological. Another example is the Laughlin fractional quantum Hall state in 2+1 dimensions, which is described by abelian Chern-Simons theory. It has a ZK one-form symmetry. Naively, the fusion of these operators should just satisfy the ZK group law, but because of the fact that flux carries charge, they fail to commute with each other, and the representations of this algebra tell us about the ground states of the Laughlin state on a non-trivial space. So now I need to address this star here. So there's actually an error in my review article, or at least in the version that before I replaced it the other day, which is that spontaneous symmetry breaking of a discrete one-form symmetry actually does not imply topological order. There's a counterexample. The counterexample is very similar to the toric code. So the degrees of freedom live on the links of some chain complex, and there are two terms in the Hamiltonian, a plaquette term, which is the same as in the toric code, and a star term, which is a one-parameter deformation of the star term in the toric code. And as a function of this parameter beta, so when beta goes to 0, it's just the toric code. But when there's a critical value of beta beyond which the topological order is destroyed, but here are a few facts. For every value of beta, for every ground state of the toric code, there's a ground state of this model, obtained by acting with this combination of operators. And for every value of beta, this system still spontaneously breaks a Z2 one-form symmetry generated by this, the same one one of them as in the toric code, because there's an expectation, a charged operator has a perimeter law. But for beta bigger than beta C, these ground states are actually distinguishable by local operators. So just because you can get from one to the other by a non-local operator doesn't mean that there isn't some way to distinguish them by local operators. In fact, they have non-zero magnetization. And actually, this example is brought to my attention by the fact that a state with similar properties arises upon subjecting the toric code to decoherence. So very famously, the toric code phase survives a finite threshold of being subjected to noise, but beyond that, it reaches a state that's very similar to this. Okay, so the extra ingredient to have topological order starting from spontaneous breaking a higher form symmetry is that it needs to be anomalous. And so what do I mean by an anomaly of a higher form symmetry? Well, I said an anomaly is an obstruction to gauging the symmetry. And what would it mean to gauge this higher form symmetry? Let's think about the case of 2 + 1 dimensions. Gauging a symmetry means summing over the background fields. And in this case, the background fields are chemical potentials for the insertion of these symmetry operators, which are the world lines of the anions. And inserting a gas of such things means that we're condensing those particles. Condensing the particles means that we're studying a wave function, which is a many-body wave function, which is essentially 1, which is a bosonic wave function. So obviously we can only do this if these anions are bosons. If these particles have non-trivial mutual statistics, it's a mixed anomaly. And in fact, the generalized symmetry that emerges in a ground state with topological order is always anomalous. In fact, this is a theorem of entanglement bootstrap called braiding non-degeneracy, that every anion always braids non-trivially with some other anion. There's always such a mixed anomaly. Okay, so there's one place where this analogy between ordinary symmetries and higher form symmetries fails, which is about their robustness. So we're used to the idea, and in fact in high energy physics people often call emergent symmetries accidental, probably because of this, that the consequence of approximate symmetries are approximate. And so you might say, well, I just told you that the photon is massless because there are no magnetic monopoles. Does that mean that if there's a very heavy magnetic monopole that the photon should have a very small mass? And in fact the answer is no. And there are various ways to see this, but the basic reason is that the operators that are charged under the symmetry that you would add to the Lagrangian to break it are non-local operators, and so you can't add them to the Lagrangian. And so the general conclusion is that higher form symmetries, at least in condensed matter physics, are rarely exact. There are special points in the parameter space where they're exact. Generally, they emerge. But when they emerge, their consequences are much more robust. So for example, in the case of the Torah code Hamiltonian is a very special Hamiltonian, but it's a representative of a phase of matter. This ground state degeneracy on the torus is a stable property. And so there's a special point here, which is the Torah code, but it's representative of a phase. However, it's not entirely stable in the sense that if I put it at any finite temperature, it becomes adiabatically connected to the infinite temperature phase. It's instantly trivial. And this is an annoying thing for people who want to use the Torah code to, say, store quantum information. There are actually topological orders that are stable at finite temperature. For example, any system that spontaneously breaks a 2-form symmetry will be stable at finite temperature because if you put it on a thermal circle, it still has a 1-form symmetry. It's a very interesting question. It's motivated a lot of progress to ask whether there's any stable, but in order to have a non-trivial 2-form symmetry, we need to live in 4 spatial dimensions, which Google probably can't do. And so it's a very interesting question whether there exists stable topological order at finite temperature in 3 or fewer spatial dimensions. Okay, so a few quick applications of this perspective. I just said that usually higher form symmetries are emergent, but nevertheless we can consider the space of Hamiltonians where they're exact. One reason to do this is that then we can define SPTs protected by them. A perhaps better reason is that although we know lattice models that realize that realize many topological ordered phases that allow gapped boundaries, if, for example, we have a topological order that has chiral edge modes, it doesn't admit any gapped boundary, and it's much more difficult to construct. There's actually a theorem that obstructs the construction of exactly solvable models that realize such phases, and this idea has led to some generalizations of Kataya's honeycomb model, which provides a systematic construction of some such phases. Okay, we can ask what is the analog of mean field theory, the workhorse of using the Landau paradigm for ordinary symmetries, and it seems to be some sort of kind of field theory where the fields create strings or membranes, and this idea has been, I think, kind of fruitful in that it gives us a new perspective on phase transitions of gauge theories, for example, on the lattice, and it's led to a homotopy classification of the old-fashioned notion of topological defects, meaning field configurations whose stability is protected by topology. And I think it has more to say about the question of what we really mean by the gauge theory. Okay, I'm going to skip that. So far, the only way in which I've generalized symmetry is by increasing the codimension in space-time of the topological operators. So here's a table from Shuhang that suggests 2 other very important ways in which we can generalize. And the first one is, well, certainly if we give up, if I'm talking about condensed matter physics, it's not obvious that I should be talking about Lorentz invariance. And so why should I be talking about fully topological operators? Let's think about operators which are commute with the Hamiltonian, but which are not necessarily fully topological. For example, we could have independent symmetries acting on different rigid slices of space. And so such a thing is called a subsystem symmetry. And one thing you can see is that operators that are charged in such a symmetry are stuck to the subspace where the symmetry acts. These are called fractons, excitations of limited mobility. And this has been a very interesting generalization. For one thing, gapped phase, non-trivial gapped phases that realize this are counterexamples to the lore that the low energy theory of a gap phase is always described by a topological field theory. And indeed, such things were discovered as part of this quest for low-dimensional finite temperature quantum memory. And they really problematize notions of what we mean by phases of matter. I guess the real issue is, what do we mean by the renormalization group? Has been a question that has required some hard thought. But let me give some very simple examples of fracton phases. The first thing we could think about doing is just taking layers of 2 plus 1 dimensional topological order, for example, some Laughlin phases, Laughlin states described by this abelian Chern-Simons theory in each layer, labeled by some k. And in this case, if we put the system on a torus, we'll get a ground state degeneracy that grows exponentially with the number of layers, because each layer has a ground state degeneracy. But we can do something more interesting if we allow the layers to interact with each other. We could think about, instead of this diagonal K matrix up there, we could think about some K matrix which is only quasi-diagonal, which is diagonal then with some nearest neighbor entries. In that case, we find a very interesting thing where the log of the ground state degeneracy depends on some number theoretic properties of L. The excitations are still stuck in the layers, but they can have actually non-trivial breeding between the layers that doesn't fall off very rapidly with the distance. Okay, there are also more isotropic examples, but I think this one is very easy to explain just by thinking about Chern-Simons theory. This idea of subsystem symmetries is actually quite useful more generally. Consider the following example. Think about a bunch of layers of Fermi liquid, 2D Fermi liquids, with the property that each layer independently conserves the particle number. So the electrons aren't allowed to tunnel between the layers, but then we can couple them by some kind of density interaction between the layers that drives this kind of interlayer exciton condensate that spontaneously breaks the separate U1 symmetries in each layer. And because the Goldstone modes for this kind of subsystem symmetry are really weird, their coupling to the quasi-particles in each layer actually, it destroys the quasi-particles and leads to a kind of non-Fermi liquid that usually requires some kind of fractionalization to construct. Okay, so far when talking about some subsystem symmetries, I've been talking about symmetries that act independently on like planes, but actually there can be systems, even translation invariant systems, where the symmetries act on a much more interesting subspace. For example, this Newman-Moore model is a translation invariant system on the triangular lattice, which has symmetries which act only on fractals. And in fact, there's a translation invariant Hamiltonian which has a symmetry which acts on that pattern there. I defy you to find some structure in that pattern. And in fact, this sort of, I guess it could be called a Cantor symmetry, is a crucial ingredient in the current best attempt to construct a finite temperature quantum memory. Okay, so then the final generalization that I want to mention is that we can give up on a group law. We can think about non-invertible symmetries where instead the fusion rule is some fusion algebra, non-trivial fusion algebra, and this generalization is crucial for realizing the most general topological order as spontaneous symmetry breaking, or non-abelian topological order. Okay, so I want to mention an application of non-invertible symmetries by condensed matter physicists to a field theory that's very familiar to everyone, I think, namely nonlinear sigma models. So I mentioned earlier that if we spontaneously break a U1 symmetry, we get a higher form symmetry, but if we instead spontaneously break some more complicated thing, so that we have a nonlinear sigma model and some more general manifold M, it in general has a non-invertible symmetry, which is described in this green text. And these folks applied this symmetry to the case of the S2 nonlinear sigma model in 3 plus 1 dimensions, and they found something quite surprising, which is that the low energy physics that's required by this symmetry disagrees with both large N generalizations, treating the S2 as n equals 2 of Sn and treating it as n equals 2 of Cpn minus 1. both predict different answers from what they found, which is axion electrodynamics. So this was an example of learning something about familiar field theory by thinking about this kind of fancy symmetry from I guess I would be remiss in this review if I didn't mention that a perspective that people like on such symmetries is to think about the symmetry action on a d-dimensional quantum field theory as encoded in a topological field theory in one higher dimension that admits a gap boundary and a boundary realizing the field theory of interest. And the defect operators of that field theory act then on the CFT, on this theory Q, whatever it is. And this picture makes duality transformations very, very, very convenient. And one reason that you might care about this is that possible gap boundaries of this topological field theory very plausibly are in one-to-one correspondence with possible gapped phases in d dimensions with the associated symmetry. And I think other people will say a little more about this. In particular, Xie will say a little more about this. So, I've I think incorporated many of these apparent exceptions of the Landau paradigm into this suitably generalized paradigm. I want to talk about two more exceptions in the last few minutes. The first is superconductors. So, although in the literature you'll find many confused statements that speak about superconductors as having something to do with symmetry breaking, the Higgs phase of a gauge theory a priori doesn't break any symmetries, so we can ask, how is a Higgs phase of a gauge theory different from a vegetable? And sometimes it's not, but if the system has a magnetic higher form symmetry, if there are no monopoles, and the condensate of the Higgs phase is charged under some other symmetry, then the Higgs phase is in fact an SPT for the product of those two symmetries, in the sense that there's an effective action for background fields for those symmetries, which has a non-trivial anomaly in a space with boundary. It has a non-trivial SPT response, and this action actually, in fact, reproduces much of the phenomenology of superconductors. Okay, and then since Joe Polchinski's answer to his titular question, what is string theory, was topological Fermi liquid on twistor space, I feel comfortable talking about Fermi surfaces at the strings meeting. A Fermi liquid, and more generally states with a Fermi surface, are examples of gapless phases. Despite the fact that they have all these gapless degrees of freedom on a Fermi surface, they're nevertheless robust to deformations of the parameters. And this robustness is usually attributed to a combination of lattice translation symmetry and charge conservation, the combination of which allows us to define a filling fraction. And in states where this filling fraction can be continuously tuned without changing the phase, such states are called compressible, these folks, Else, Thorngren, and Senfel, proved that this means that the system must have a very large emergent symmetry, larger than any compact Lie group. And in 2 + 1 dimensions, essentially the only way we know how to saturate their LSM theorem is if the system has an independent conservation law of particle number at each point on the Fermi surface. So this is called LU1 symmetry, meaning a symmetry transformation is labeled by a map from the circle to the Fermi surface. And the consequences of this symmetry actually, by anomaly matching, reproduce, again, much of the phenomenology of systems with Fermi surfaces, both Fermi liquids and what they call ersatz Fermi liquids, which includes, I think, every known non-Fermi liquid. I want to mention a very strange consequence of this, which I encountered recently with Thur and Grover, with whom we've been studying the phase transition from a liquid Fermi liquid to a solid phase, so that the system spontaneously breaks translation invariance. And at the transition, the transition is a non-Fermi liquid described by the Fermi surface coupled to a Bose surface, meaning a collection of bosonic modes, which are gapless modes on a ring in momentum space, which couple different points on the Fermi surface. And it's a compressible state, and this theorem seems to say that it has to have this LU1 symmetry, but the different points on the Fermi surface definitely don't decouple from each other. They're very strongly coupled by these bosonic modes, and the only way it can have this symmetry is if the symmetry also acts on these bosonic modes as if they were matrices labeled by the points on the Fermi surface that they connect. So I think, yeah, this very exotic symmetry structure seems extremely interesting to me. Okay, so I've tried to, I can't actually see that, but I assume it says 0. Oh, 5 minutes. Oh, okay, I think I'm going to finish a little early. Good. So the question that I've tried to discuss is whether a suitably enlarged Landau paradigm, including all generalizations of symmetries that we know about, and using them properly, meaning including their anomalies, incorporates all phases of matter. And there's a further question we can ask, which is whether it also incorporates transitions between them. That's also part of the Landau paradigm, that the transitions between phases should be the degrees of freedom there. The critical degrees of freedom should be fluctuations of the order parameter. And Xie will say something about that in her talk. Whether we can understand all these things as consequences of symmetry. So the things in, well, okay, at least some of the things in blue, I said something possibly useful about. I think we can come up with some more counterexamples, and this activity of coming up with more possible counterexamples to this picture of the world has actually been a pretty fruitful thing to do. And Landau seems to actually have been pretty correct, more correct than even he probably thought. Okay, that's the end.
So we have principle 5 minutes, perhaps even a little more, given that John was only took 36 minutes for questions for John's talk.
Yeah, so what about superconductors that are not SPTs?
Right. So indeed, according to what I said, yeah, not every superconductor is an SPT. I guess maybe I should mention, in the real world, superconductors are all the condensate is always charged 2, and so there's always a Z2 subgroup of the electromagnetism that's unbroken, and so they're always in that case there's still topological order. So that does distinguish them from the trivial phase. But you could imagine if there were charge 1 degrees of freedom that wanted to condense, such a superconductor could be a complete vegetable. Yeah.
Thanks.
Hi. I'd like to ask about that counterexample to the spontaneous symmetry breaking of one-form symmetry.
Yeah, it's pretty interesting.
Yeah, I would just like to ask you to talk more about it. And could you say, in field theory language, what the low energy limit is, or maybe describe that transition, if possible, in field theory?
Yeah, I think the transition is not something. It's a transition that we know. The critical theory of the transition is a familiar thing. I think probably it's still Ising. In fact, yeah, it is Ising because in this model actually it spontaneously breaks a Z2 symmetry at the transition. Yeah, so that in itself, the transition itself is I don't think teaches us something too new. But the phase that it goes to is kind of strange in that although it looks, so the states, there is a ground state degeneracy and the states are related by the action of some non-local operators, but they're nevertheless distinguishable by local operators. They have different magnetizations. Yeah, maybe I should say, actually, here's maybe one useful thing I can say. You can understand what this star term, this deformation of the star term does. So the star term of the Torah code is just the condition that the strings don't end. But with this deformation, so the ground state of the Torah code is a uniform superposition of closed strings. With this deformation, instead the strings are weighted by something that depends on their area, I believe. if I'm remembering correctly. And so the states with different, in different winding sectors actually have different magnetizations for just like the symmetry that flips the Z's. So yes, okay, that wasn't a field theory answer, and I don't have a good field theory answer, but that's my understanding.
John, can you comment on the can you comment on the Wigner crystal phase transition in the quantum Hall system at low filling fractions?
Okay. So the question was about so in quantum Hall systems, there's another phase in 2D electron gas, another phase that's realized in addition to Fermi liquids and fractional quantum Hall states is a Wigner crystal. Yeah, so we can ask about, that state itself is characterized by spontaneously breaking translation symmetry, so it's definitely within the Landau paradigm. But indeed, we could think about the transition, and I guess this is a subject that I'm very sensitive to because of this project I mentioned with Tarun, where there's a piece of lore that solidification transitions are always first order, and there are a few good reasons to think that. One is that you can write a Landau theory where if the lattice that's forming contains triangles in the reciprocal lattice, if you can make a triangle out of the reciprocal lattice vectors, as you can, for example, for the triangular lattice, which is what Wigner crystals in 2 dimensions usually are, then there's a cubic term in the Landau theory, and so perhaps that suggests that it's at least weakly first order. But nevertheless, so even if that's true, we can ask about the critical point where that cubic term goes away, and so I do think that there's an interesting story about solidification transitions. Which I suppose I am, in all of the words I was saying, I was using a Landau perspective in that I was writing an action for the degrees of freedom at the transition, which are exactly the fluctuations of the density, which is the order parameter for the transition. I would say that it's, I think, an interesting subject, but firmly within the scope of Landau's ambit.
So, any questions from Zoom?
There was one question that was typed by an anonymous attendee. Do you have any insights if curvature may play a role in phase transitions?
Okay, the question is about the role of curvature in phase transitions. I'm not sure if I have anything interesting to say about that. Curvature does certainly play a role in our understanding of the classification of SPTs. Some of the non-triviality of some such phases does require coupling to background fields involving the structure of space-time. Well, I will say that I'm very excited about the fuzzy sphere regularization of CFT. That's an example of the role of curvature in critical theories.
Okay, we can thank John again. And now we'll proceed with the 3 5-minute presentation. We'll start with Xie Chen from Caltech.
Good morning, everyone. My name is Xie Chen. I am a condensed matter theorist, so it's an honor to be here and talking to everyone. Since I only have 5 minutes and I'm asked to wait for 2 minutes, so I'll take advantage of these 2 minutes by starting to talk to you about what I plan to say, just in case I run out of time. So I plan to follow up with John. John was talking about how this framework of generalized symmetry help us to expand upon the traditional conventional Landau paradigm to study phase and phase transitions. So I want to say a bit more about how, that's not my slides. That's not my slides. Sorry. To say a bit more about how this framework helps us to think hopefully more systematically about phase transitions, and in some way have a more generalized framework for Landau paradigm, but for phase transitions. So in particular, I'm going to invoke more the symmetry TFT framework. I think it emerged out of more or less this community, and say how that can help us to make connections between different phase transitions and see their relation among them. Right, that's my slides. Great. So I'm going. So I put a sandwich here. This is the symmetry TFT framework that I have in mind. It's edible, and then so my title is Generalized Symmetry and Beyond Landau Phase Transitions. Okay, great. So yeah. So the traditional Landau paradigm is about phases characterized by breaking of the symmetry, and the transition characterized by the breaking of the symmetry as well. So we have one side that is more symmetric, and the other side that is more symmetry breaking. And at the transition, it's the order parameter that fluctuates, and then we can write down a low-energy field theory for it, and all the story follows from there. So that works. That kind of description of a transition applies to, let's say, a simple symmetric phase to a simple symmetry breaking phase, or an SPT phase to a simple symmetry breaking phase. But for all the other phase transitions, this paradigm breaks down. Just the naive application of it breaks down, right? We can have all sorts of phases that John was just talking about, and try to say, what does the phase transition look like? And it's not obvious how to apply the conventional Landau paradigm to it. But luckily, if we think of some of the topological phases in terms of higher form symmetry breaking, then we can have some kind of a similar story of a higher order parameter fluctuating, and John was presenting some mean field theory for it. So that kind of characterized the topological transition, some of it also in this paradigm. But then we also have others, like transition between different symmetry breaking phases where the symmetries are non-compatible, or different SPT phases, or different topological phases where all that kind of symmetry phase transitions follow along a similar symmetry breaking paradigm. So my message is trying to say that maybe it's, yes, to some extent, not the full extent, but to some extent maybe it's this the symmetry breaking pattern applies more generally than we originally thought. And case by case, actually, we already know a lot of examples where non-traditional Landau transitions can be mapped to symmetry breaking transitions. For example, in 1+1D, when we talk about Majorana fermion chain, the transition between different P-wave superconductors famously can be Jordan-Wigner transition into a Z2 symmetry breaking phase. And then we can have 1+1D SPT phases with Z2 cross Z2 symmetry. Then there's a famous Kennedy-Tasaki transition that maps it into also symmetry breaking transition. And then there's a 1+1D so-called DQCP transition. That's a jargon from condensed matter, but basically means incompatible symmetry breaking phases where the transition is mapped to a Z4 symmetry breaking phase. And then I can give more examples. For example, sorry, why is going the other way? There are also other examples more lately discovered involving non-abelian symmetry groups where all these beyond Landau transitions are mapped to symmetry breaking transitions. So what I'm trying to say is that using the symmetry TFT picture, actually we can understand all these mappings between phase transition theories in a very uniformed way. And maybe that uniform picture is a guiding way to think about transitions in a more systematic framework. So basically, this is my picture of what symmetry TFT, the sandwich structure, looks like. We have a bulk theory that's topological, a D plus 1D TQFT, with a top boundary that's gapped. And usually we say some fractional anion condensed on the top boundary. That's the topological boundary. And then things happen at the bottom boundary where all the dynamics happen. And in particular, we can choose a TQFT with a certain kind of condensate on the top boundary, and then which determines the symmetry of the sandwich. And then on the bottom boundary, we can choose to transition between an A condensate and a B condensate representing different phases, and then the transition will give us the phase transition, right? So all of the previous examples that I showed actually correspond to the following transformation in the symmetry TFT picture, where we just start from an arbitrary condensate at the top boundary and change it into one of the condensate at the bottom boundary. And that allows us to do Jordan-Wigner, Tenney-Tasaki, and all the transformations I just showed you before. And when this is helpful, and this actually makes all the transitions into a symmetry breaking transition, because the top boundary matches with one of the phases we're trying to transition into, such that anions can tunnel in between the top and bottom boundary on one side of the transition, and that becomes the autoparameter of that phase. And this autoparameter, it's charged under the horizontal symmetry operator, so it actually tells us that the right-hand side is the symmetry breaking phase, the left-hand side is the non-symmetry breaking phase. So this becomes a symmetry breaking story. The only caveat is that the symmetry can be potentially a generalized symmetry. So once we embrace this notion of generalized symmetry, we can think of all these phase transitions as kind of symmetry breaking transition. Okay, so that's kind of my 5-minute message. And what I'm trying to say is that this symmetry TFT picture gives us a maybe more systematic way to think about phase transitions. Rather than just from symmetric phase to symmetry breaking phase, we should think of phase transitions as the competition between two condensates at the boundary of a TQFT. And then it inherits all the topological, categorical symmetry from the bulk. And then we can, in this more general framework, ask the very, very basic questions, like, are all such transitions continuous? Because within the traditional Landau paradigm, only the very simplistic symmetry breaking transitions are naturally continuous. But within this general framework, maybe all such transitions are continuous. And then maybe all such transitions can be dual to some kind of generalized symmetry breaking transitions. Of course, whether what I'm saying here makes any sense or is useful depends on whether we can actually write down effective field theory and then try to extract universal properties from there. But that's a lot of work to be done. So yeah, thank you. That's all I want to say.
So one urgent question, mostly for clarification now, otherwise we'll postpone it at the end. I don't see any hands up, so we can thank Xie again and proceed. The next panelist is Meng Cheng from Yale.
Okay, so good morning, everyone. My name is Meng Cheng. And, well, the slides come out without any problem. So I'm going to tell you a little bit about how this development at the interface between condensed matter and high-energy theory has sort of reshaped our understanding of symmetries and anomalies in lattice models, in condensed matter systems. Okay? So let's see whether I can transition to the next slide. All right, so a central theme in condensed matter physics is to understand the emergence of collective behaviors in quantum manifold systems. In other words, we're really going from UV systems to IR dynamics, to IR phases. And the typical sort of condensed matter systems in solid states, for example, can often be modeled by fermions or spins living in a lattice. And the kind of global symmetries that we will see in such systems, the robust common global symmetries, are more or less listed here. You have charge or spin conservations, you have time reversal symmetry, and you have lattice symmetries. And they can be broken by further perturbations, but at least most of the time they are good starting points. Okay. And generically, there are no exact higher form or non-invertible symmetries in lattice models in UV, except at special points in the parameter space where these generalized symmetries can be exact. And many examples have been studied in 1+1D and 2+1D, and I guess you'll hear more about them probably in the conference. Okay, so an important insight coming from this interplay between the different communities is that now we understand even these garden variety systems, which describe realistic materials, can have anomalies in the UV. Okay? So the anomalies come about because of the interplay between the internal symmetries and the lattice symmetries. So each of them doesn't have any anomaly, but when you have both of them and under certain conditions about how they are represented in the UV, they can have mixed anomalies. So let me give you two examples. So one of them is called the fitting anomaly. So this happens in a translation invariant lattice system with charge conservation symmetry and a fractional fitting factor. So fitting factor just means the average amount of charge per unit cell. And if that's a fraction, then you have anomaly in this system. And the second example is a Lipschitz-Mattis anomaly, where similarly you have translation invariant lattice with now spin rotation symmetry, SO3, and half integer spin per unit cell. In that case, you also have anomaly. All right, so as is well known to its audience, anomalies constrain IR dynamics. So understanding of this anomaly in the UV allows us to sort of answer the following question. Given a particular UV system, here by UV system I mean a certain lattice, a Hilbert space plus a global symmetry, what are the possible IR faces? Okay. And of course, to answer this question, you have to make some assumption about IR dynamics. And the most well understood case is when the IR physics is described by a quantum field theory with emergent Lorentz symmetry. So let me focus on this case, even though there are many notable exceptions to this assumption. Okay. So this problem is also kind of known as a classification of symmetry enriched faces. And by now, there's sort of a general framework to answer this sort of questions. And not going into details, the answer depends on how the UV symmetries act on the IR degree of freedom. So I'll skip all of these things. You'll see more about this from Maissam's talk. And let me just give you one example to illustrate this formalism. So let's think about a system of spins, some lattice of spins, where the interactions preserve spin rotation and lattice translation symmetries. This can describe many heuristic magnetic materials. And there are many, so this system has a Lipschitz-Mattis anomaly. In the IR, there are many options, but one of them could be a topological quantum field theory, such as a U1 level 2 transassignment theory. So again, without really going into details, I just want to highlight the feature that in the UV, we only have zero form symmetries in such a kind of a garden variety lattice model. But in IR, what's really important are the one form symmetries. So the UV zero form symmetries act on the IR through the one form symmetries by the mechanism known as symmetry fractionalization in the condensed matter literature, in such a way that the UV Lipschitz-Mattis anomaly is realized through this mapping. Okay, so of course that's not the only way that the IR, that's not the only possible IR faces, but due to anomaly, all of them have to be non-trivial in some way or another. Okay? So this brings me to a last point that is also interesting to understand what happens, the implication of the anomaly, not just through some particular IR dynamics, but more generally, how they impact the structure of correlations and entanglement of the states invariant under the symmetry. Okay? And this really comes back to a definition of anomaly in the lattice model, in the UV, where you don't necessarily have any sort of field theory framework to work with. So one working definition of anomaly is that just it prevents you from having any sort of short-range entangled states in the UV. And we can just think of a short-range entangled state as a trivial product state up to some local deformation. But we can ask for more. We can ask, for example, how does anomaly constrain the structure of entanglement through a notion of a multipartite separability. So roughly speaking, this is about the following question. So if you have a given partition of a system, the separability is about whether the state can be tensor factorized according to this partition. And as it turns out, anomaly sometimes prevents you from writing a state into such a tensor product factorized form. Okay? For example, in 1 plus 1D, if you have zero form anomalous symmetry, then you don't have tripartite separability, but the state can be bipartite separate. I do have a last slide. It went over too much. Sorry. Okay, I guess I don't really have any time to talk through this slide, but this dialogue between lattice and continuum has been extremely fruitful, and I hope it will continue to provide us with more insights on both sides.
Thank you.
Thank you.
Any immediate question for Meng? Okay, if not, we'll thank him again. And proceed with Maissam Barkeshli, who is the last panelist from University of Maryland.
Okay, so thanks for the invitation. In condensed matter physics, we're often interested in this question of we have some kind of UV system, and we're interested in what are the possible phases of matter that are realized. And typically, we have a situation where we have some symmetry group that I'll call G or GUV. And in general, there's some IR fixed point that governs the universal behavior of the system. That could be a topological quantum field theory, a conformal field theory, or something more complicated. And that fixed point theory has its own symmetry group, as Meng was discussing, which I'll call the infrared symmetry group, which contains the internal and the space-time symmetries of the theory. And so one thing that's very important is there's a group homomorphism that maps the UV symmetry into the symmetry of the IR fixed points. Okay? And in many cases, there's only a discrete set of possible choices for this group homomorphism. So we actually should be viewing this group homomorphism as a kind of invariant of the UV in those situations because it's invariant to deformations of the UV theory. Okay, so this means that actually we don't have a single renormalization group flow from the UV to the IR. We should imagine that we have a collection of renormalization group flows because in the UV we can consider various networks of symmetry defects, and for each network of symmetry defects there's an RG flow that maps us to the IR where the symmetry defects are in the image of that homomorphism. So this means that we can actually have theories, different UV theories that have the same exact IR fixed points, but they differ by this group homomorphism. And so this opens up the subject of symmetry enriched phases of matter. The UV could be separated by some phase transition, even though the fixed point is the same, because we have different group homomorphisms. But it turns out this is really only the tip of the iceberg, because the IR symmetry is actually in general not a group. Okay, so for example, for a D plus one-dimensional topological quantum field theory, we now expect that the IR symmetry forms a much more complicated structure, a fusion D category. And the way that we understand this is from this general correspondence between symmetry and topological defects. And basically, this higher category is characterizing all the topological defects of varying codimension and their mutual interaction. Okay, so let me give you a taste of what that looks like. So in the higher category language, there's zero morphisms, one morphisms, two morphisms, and so on. So we'll think about the zero morphisms as codimension one defects in the system. These would be like domain walls or gapped domain walls in a topological phase. The one morphisms would be domain walls between the domain walls. The two morphisms would be domain walls between domain walls between domain walls. Those would give us codimension three defects. And then we keep going until we get to D morphisms, which physically correspond to codimension D plus one defects, which are point-like defects in space-time. But there's a lot more structure still because we have this fusion structure. So we can take tensor products of all of the morphisms. So we can have fusion for the domain walls. The fusion structure allows us to consider junctions of the one morphisms. Then we can have maps between different kinds of networks of junctions. Those would be one level higher, and so on. So for example, one situation that we work with quite a bit in condensed matter physics is the situation of 2+1D gap topological phases of matter. So there, the IRTQFT has some categorical symmetry. We've known for a long time that there's a modular tensor category that describes the anyons. In addition, there's a lot more data as well if you want the full symmetry structure. For example, there's a zero-form invertible symmetry, which is the group of braided autoequivalences of the modular tensor category. There's yet more data. We can consider junctions of the domain walls, and we can ask about what happens when we pass lines through the junctions. That gives even more data. And then it keeps going. For example, we could have those codimension 1 defects end at codimension 2 defects, and we could be thinking about fusion and braiding structure of those higher codimension defects. We could be thinking about non-invertible domain walls, and so on. Okay, so now if we come back and try to ask this question about symmetry-enriched phases of matter, we actually should also be viewing the original group in the condensed matter system as a higher category. So in the UV, we can not only have domain walls, but we can have junctions of domain walls, and then we can have maps between more complicated configurations, and so on. So if we want to describe symmetry-enriched phases of matter, we should actually be thinking of some higher homomorphism. So we should be thinking of our group as a higher structure, like some kind of invertible fusion D category, and we'll have a higher homomorphism that maps into the invertible part of that higher fusion category that describes the symmetry of the IR fixed points. So if we specialize to the case of 2+1D symmetry-enriched gapped phases of matter, this is the situation where we have most amount of experience over the last decade. That gives the framework of G-crossed braided tensor categories, which we've spent a lot of time studying quite systematically. And so the message that I want to convey is that we can basically understand all topological phases of matter from this perspective. Symmetry-protected topological states, topological insulators, fractional quantum Hall states, quantum spin liquids, anomalies. These all can be couched in this very general formalism, and as such, it's extremely powerful. Okay, so I would say that the data that characterizes a symmetry-enriched phase would be this higher fusion category together with this higher homomorphism. Okay, so just a few things, there's a number of things that I think are interesting going forward. One is there's a lot of situations where mathematicians have this higher categorical structures, and it's extremely abstract. Even they call it abstract nonsense. But I think it's a job for physicists to make these very concrete into some concrete set of algebraic data, equivalence relations, consistency conditions, which is very fruitful for doing calculations. It's also very important to relate these mathematical structures to the operator algebra that describes the UV lattice model or the quantum field theory more generally. And there's a number of questions that I think maybe we can leave for the discussion section, but I'll just put up there. Thank you.
Thank you, Maissam. One immediate question for Maissam, if any, and meanwhile I would like to invite John and all the panelists, Xie and Meng, to go up. Okay, so this is a bit of an experiment. It's a new format. So the overarching theme, of course, is symmetry, global symmetry from the perspective of condensed matter, and hopefully that is teaching us some lessons for us continuum quantum field theorists and high energy people. And so let's have a first round of the panel with this perhaps unfair question, which is, what is symmetry? And what can you tell us that we didn't know? And I think John had prepared some slides about this to introduce the theme.
Can you put my slides back? Excellent. Okay, great, thank you. We had a little bit of warning that this question might come up. So yeah, let's think a little bit about what is the symmetry of a quantum let's think a little bit about what is the symmetry of a quantum many-body system. I'm going to think about it from a canonical point of view, meaning pick a time slice, and suppose we have some Hilbert space and some Hamiltonian. What do we need to say that there's a symmetry? So I think maybe it should be a collection of operators that commute with the Hamiltonian. Oops. Okay, I really like that one. The second condition I'd like to impose is really, my motivation for imposing it is to rule out the first condition is satisfied by projectors onto eigenstates of the Hamiltonian, and that's not a useful symmetry. So a problem that those projectors have is that if you conjugate a local operator by such a thing, you get something that's not a local operator. So one way to rule out such things is to demand that when we conjugate local operators by our thing that we're going to call a symmetry, that it should still be local, maybe it doesn't have to be zero range, maybe it can grow a little bit. I think there's some room to discuss that. And then the third condition that I really, really, really want is that it should act non-trivially on the Hilbert space. I would like to take this opportunity to say that I don't think there is any good reason to ever use the phrase gauge symmetry. A gauge symmetry is not a symmetry. A gauge invariance is not a symmetry. So that's not what I'm talking about. And then finally, there are three more conditions here that we don't need, which I guess I already talked about earlier. So U can be supported on somewhere other than the whole constant time slice. It doesn't need to satisfy a group law. It doesn't need to represent a group or even projectively, and it doesn't need to be unitary. So there's another demand that especially in the HepTH literature, has been used really fruitfully, which is demanding, well, okay, so, yeah, okay, I guess there are two questions I want to ask about this list. So one is, I certainly haven't said here that U is topological. So it could be that, just from what I've said, that it follows that U should be fully topological. I think that's not true. And if it's not fully topological, there's another question we can ask, which is, can it be used as a defect operator? Meaning, rather than inserting it at a constant time, can we insert it in such a way that it twists the Hilbert space to make twisted sectors? And it could be that the demand of locality preserving is enough to guarantee this. If, for example, U is actually a quantum circuit, a product of local unitaries, then I think we do know how to make a defect operator. But some locality preserving operators, like say translations, are what are called non-trivial quantum cellular automata, and the main property of such things is that they can't be so truncated like a circuit. And then, okay, so I just have one more thing to say, which is I don't think even in systems with Lorentz invariance in the continuum that we all love, it's true that all symmetries are topological operators. And I have in mind a very specific example. It's probably a little too specific, which is in 1 + 1 dimensional CFT. So the Virasoro generators are not symmetries, according to the definition I just gave, because they don't commute with the Hamiltonian. Rather, they're spectrum generating operators. But these folks constructed a tower of operators that do commute with the Hamiltonian, and which are local operators, so that it's an integral over space of some powers of the stress tensor. So they are locality preserving, but it seems that these operators are in fact not topological. So yeah, and this actually was pointed out to me by Xie Zhang, who's a student of Ken Trilligator, who's graduating this year. Yeah, okay. That's what I wanted to say.
Okay, thank you. So I'm sure your colleagues have opinions. Maybe we go in order, Maissam.
I have one thing that actually bothers me about this question, and it's related to the last thing that John talked about in his talk, which is there was this example of understanding the Fermi surface and Fermi liquids from the perspective of symmetry, where the idea was to think of it as having this emergent LU1 symmetry. And the LU1 came from having smooth maps from the Fermi surface into U1 in 2 dimensions. And the strange thing about that example is that it appears to be extremely useful to think about that LU1 as a symmetry, but it's actually not a symmetry according to the 2 conditions that John gave in that slide, because that generally does not take local operators in real space to local operators. So it becomes a question of, is there a fruitful way of relaxing that condition or making it more precise? Like, should we say that operators with bounded support get mapped under symmetry to operators with bounded support? Or should we be relaxing that condition? Or how should we be thinking about it? Because that example of the LU1 symmetry of the Fermi surface does not fit into that. But nevertheless, it's extremely fruitful. So I think I don't have an answer to what is symmetry, but I have a frustration in that particular example.
Meng?
Yeah, perhaps I can elaborate a little more on this point of locality preserving. That is certain property that we want on global symmetries in a many-body system with structural locality. Right? Otherwise, Wigner answers all the questions for us. I'm used to think about lattice system with a clear UV regularization. In that case, it's actually perhaps more explicit and easier to define what it means to preserve locality. And in particular, if we just think about bounded operators or operators with finite support on a lattice, then we can just look for automorphisms of the algebra of all such local operators, and we can call that as a symmetry. Okay? But in one dimension, it turns out that this sort of automorphism have been studied a lot in quantum information community, and we know basically there's a clear classification of such automorphisms. If you don't impose anything else, just take a tensor product of a bunch of spins forming a spin chain, and such automorphisms always come in basically 2 kinds. Either they translate, you just have shift of one side to another, the translation, or you have a finite depth unitary, or you can compose them in arbitrary ways you like. And that certainly covers a lot of symmetries that we know, but not all of them. So one more thing you can do is to restrict that automorphism to a subalgebra, not the full matrix algebra on the spin chain. For example, you can impose some global symmetry and look at automorphism of algebras within that subspace, the operators that commute with the symmetry. And then from that, we can recover some of the non-invertible symmetries that have been studied in recent times, the Kramer-Wanier duality, this RAP-DA symmetries, etc. Many of them can be recovered this way. So it becomes a question of what exactly is the algebra that we're talking about, that we want to preserve locality, and that probably has some implication on what symmetries really mean. But even this definition of locality preserving, so this works very well in 1+1D, and there's a one sort of a side part of the definition that operators cannot be moved too far away from where it was defined. So if you try to generalize this to higher dimensions, it doesn't cover things like, even in 1D, it doesn't cover things like reflection, even though it's obviously a global symmetry. So I think here there's still some work to do to figure out what this definition really implies.
Sure. Yeah, so I totally concur with some of these points the previous panelists are making. I think eventually one of the key questions we need to answer is, what do we want to do with the generalized symmetry? There are definitely many ways, many directions we can go into, but for the purpose of studying, let's say, phase and phase transitions, if we want to, say, have an idea of a whole phase diagram, and then impose symmetries on top of that, then very crucial idea is this symmetric subalgebra. I think it's more than just operators commuting with a single Hamiltonian. It's operators commuting with a bunch of Hamiltonians with varying parameters, and that's where basically these the bunch of Hamiltonians is drawn from this parameter space of symmetric local subalgebras. So, so this very much relates to the notion of QCA and all that. And recently, actually, we have been doing some work in terms of something called sequential quantum circuit, and actually have a few slides that I want to show to just say a bit more about this idea. So can we pull up the slides? It's at the end of my other slides. Thank you. So basically, the idea is that so I'm a person that lives on lattice, and I hear about all these discussions of generalized symmetry, and I ask myself, what does that mean for me? So originally, symmetry has at least the internal symmetry has a pretty clear notion. For me, thank you, yes, perfect, but that's at the end. Okay, I'll flip to the end. Originally, that at least internal symmetry is what we call on-site symmetry, that we have a lattice, and each lattice site has a finite Hilbert space, and then this, and then the symmetry, sorry, I flipped over. Symmetry acts as tensor product of unitaries on each of the local Hilbert space. And that has a very clear structure, and it obviously preserves locality, because it's just tensor product of local operators, and obviously preserve a symmetric local subalgebra, because they're operators locally just commuting, carrying charge 0 on each lattice site. But then, of course, we get into SPTs, and then we realize, oh, there's anomalies, so not all symmetries are on-site from a lattice perspective. And for a lot of those anomalous symmetries, actually, we just need to turn it into a finite depth circuit, which means that we apply a bunch of non-overlapping unitaries, and then we apply another bunch of non-overlapping unitaries, and then that pretty much captures it. So in that sense, it's not entirely on-site, and that's where the anomaly comes from, but it's still very much locality preserving, because it's just 2 layers of unitary, and it cannot grow an operator to be very big. But then there's the notion of symmetry gets even more generalized, and then we realize that even those, like, finite depth circuit cannot achieve the purpose. For example, a very outstanding example is the so-called Kramer-Vanier duality, where we take the symmetric phase of the Z2 Ising model to the symmetry breaking phase of the Z2 Ising model, and we can ask, what is this non-invertible symmetry that does the job? And I want to do it from a lattice perspective to achieve this goal, from using local unitaries. And it turns out that, and this is known, but it turns out that this is the circuit, the kind of quantum circuit that achieves the purpose, that it has some unitary on qubit 1, 2, and another unitary on qubit 2, 3, and another qubit on qubit 3, 4. And you have to do it like step by step. You have to do it from the left-hand side, and then move one step further to the right, and then eventually sweep out the whole system and implement the so-called Kramer-Vanier duality. And this is different from the 2 previous type of symmetry that I talked about before. This is not on-site. It's not a tensor product of unitaries on each side. It's not a finite depth circuit, because we are doing many, many, many layers of circuit, even though in each layer we're just doing 1 unitary gate. But this is what we call a sequential quantum circuit, because it does go from the left-hand side and sequentially sweep out the whole system. So this structure of quantum circuit is my new understanding of what is a generalized symmetry on a lattice. It actually has this a very high depth structure, which means that it doesn't fully preserve locality, but however, it preserves the locality of a symmetric subalgebra, at least in this case, for this specific case. So from a lattice perspective, I'm trying to say that this is my new definition of what is a generalized symmetry, that I can have a sequential patterns of quantum circuit that implement the symmetry, and that connects to this topological idea because the sequential pattern is actually moving the topological defect around in the system.
Q. So about this general question, what is symmetry and whether is it always a topological operator? The audience, there's many questions here. I don't know who to pick. I will start with Lenny Susskind.
Kumran here asked me the question, what does all of this have to do with string theory? Let me just generalize that a little bit. Instead of string theory, let me say quantum gravity. So my question is, all people who think about quantum gravity will agree that ordinary symmetries, the ordinary symmetries of physics cannot coexist with gravity. Gravity somehow must break them. Is this true also of these higher form symmetries? Can the higher form symmetries coexist with gravity? Are they necessarily broken by it? I don't have an answer. Anybody up there who has an answer, or anybody here down here?
I think we should let Shuheng answer.
So this is a essential question, though this is a condensed matter panel.
This is a
I'm not sure. I'm not sure.
Theory conference.
I'm not sure they are the. So I think the consensus is that yes, in quantum gravity you also cannot have higher symmetries of any kind.
But you can have electrodynamics coexisting with gravity, and electrodynamics does have this higher form symmetry, does it not?
It does, yeah.
Then I think I
No,
disagree
no,
with
it
what
doesn't.
you said.
Yeah, no, yeah, of course, pure Maxwell. Yeah.
Right, so I guess my understanding of the consequence of this is that it means that the charge lattice should be filled out by matter. So there should be no, the gauge theories that are realized
Then how?
do have monopoles, and indeed that's what we find in string theory.
Yeah, so I guess I was going to comment on something related. Yeah, so John, you said that we should never talk about gauge symmetries, but basically along the lines of what Lenny was saying, I would say those are the only symmetries.
They're not symmetries.
Let me finish. So what would you say about asymptotic symmetries? Those are gauge symmetries, but they're real, right? That's the physical part of the gauge symmetry.
Then they're not gauge symmetries.
Maybe we don't. Maybe this is a linguistic problem.
No, it is.
So I used the word asymptotic symmetry. How do you feel about asymptotic symmetries?
I'm happy that people work on them.
But I mean, for example, you said something like, so for example, like in the Fradkin-Schenker model, right? There's no one-form symmetry because of the dynamical charges, but there's still a sharp phase boundary, and you can classify the phase boundary by using asymptotic symmetries. So you might want to think about them.
There's an emergent one-form symmetry.
No, but there's an exact asymptotic symmetry.
So my objection to this word is really just from so many years of people confusing themselves about it, and so it's true that it's a linguistic complaint. So I just think when you say, that combination of two words just causes a lot of trouble. So things that are symmetries, you should call them something else. So asymptotic symmetries or symmetries, I'm perfectly happy to. Yeah.
But I mean, nobody talked about them. We had a whole bunch of talks here, and you can use them to classify phases. So maybe we should talk about them.
I mean, I would assume that's related to what happens in this superconductor example that John discussed. This asymptotic symmetry related to what happens on the boundary of.
Yeah, that's correct. So, yeah, that's correct. That's the right way to think about it.
Tim?
Yeah, I just wanted to push back a little bit on this claim that, John, you introduced this locality preserving property in order to eliminate these projectors, but with some assumption that they are useless. But why are they useless? If we construct, let's say that we have a quantum field theory and we construct some topological operator which corresponds to a projector to some state, then we would have an energy of that state. I mean, they're only trivial if we already know the spectrum and we know the states. Why do we want to eliminate such topological operators, like projectors onto some energy states. I don't think that they're necessarily trivial. Do you understand what I mean?
Why do you say they're topological operators?
I mean, well, not necessarily topological, but they commute with the Hamiltonian.
Well, I guess what I had in mind is that any Hamiltonian has a spectrum of eigenstates. So
that's true, but I don't see why we would want to eliminate such projectors as useless.
In a many-body system, the projectors onto eigenstates in the middle of the spectrum are deeply horrible things.
Right.
That I think we have no access to them, and if we did, it wouldn't help us.
Right. I mean, maybe we don't have no access to them, but I mean, why would we want to eliminate such objects from the definition of symmetries? Because I mean, they sound like useful things to have if we could access them. So,
good luck.
I think one thing I want to comment on that is if we say, okay, the projectors onto the eigenstates are our symmetry, and let's consider the class of Hamiltonian as invariant under the symmetry, we would just add random eigenenergies to these eigenstates and form Hamiltonians, but maybe a lot of them will immediately become non-local. There's no control over the locality. And if we want to preserve the locality of the class of Hamiltonian we're considering, I think we need to impose some locality preserving condition that John talks about. That's from condensed matter perspective.
So we are basically out of time, but I really have to ask one final question. So coming from a high-energy string theory perspective, some of these discussions in theoretical condensed matter sound incredibly abstract. You guys are more mathematical than us. And so the question seems, that really comes to mind is, so is this actually good for real condensed matter in any way? Are there any new insights about real materials or other than exotic lattice systems that exhibit these structures?
Okay, I can answer that because I've been working on that very question for some time. So one thing that we're interested in condensed matter is we have some system, and typically the symmetries will involve like some U1 charge conservation, SO3 spin rotation, but then there's also things like time reversal, then lattice translations, lattice rotations. And we're interested in this question of, for example, what are all of the invariants that describe some phase of matter when you include the discrete translation, rotation symmetries, and time reversal and things like that. And when you think about those kinds of discrete crystal symmetries, it's actually very difficult to deal with them. And this formalism has been actually very useful in trying to systematically classify all possible, say, symmetry-enriched phases and figure out exactly what are the invariants and exactly what are their physical properties. So for example, there's interesting invariants, like if you have a lattice disclination, that will accumulate some fractional quantized amount of charge in a gapped state. If you have a lattice dislocation, or something similar, and there's a whole host of invariants associated with crystalline symmetry that we were able to discover using these methods, and we wouldn't have had a method to really do it without these methods. And these actually have ramifications for condensed matter systems that people are creating in the lab, like fractional churn insulators in moiré materials. It's not clear whether we'll be able to successfully measure them, but it actually does address questions that are of some experimental relevance there.
Perhaps one final comment?
Maybe I can add to the answer by invoking a little bit of history of Lipschutz-Matisse theorem. It was known for a long time, proved in 1960s by Lipschutz and Matisse in the appendix of their paper, which became the best known part of the paper. But in the original proof, there was no mention of anomaly, anything. It was just a statement about the spectrum of a spin chain, and using a lot of symmetries, continuous symmetries. So it took a long time to reformulate this Lipschutz-Matisse theorem as a statement about anomaly and lattice model. But once you have that realization, you immediately see how to generalize it to many other situations. For example, the symmetries can be broken from spin rotation to a subgroup, a time reversal symmetry or discrete subgroup, which applies to a much wider range of materials with spin-orbit coupling and relevant to discussions about realistic condensed matter solid-state systems. So I think that's one way where this point of view is really refined and generalized. Some of the knowledges which then these generalizations would be very difficult to imagine without this kind of perspective.
Okay, thank you. I think we're out of time, so we thank the panelists again, and we will reconvene at 11:10.